Hi, everyone. We're going to look at the fourth set of notes in our bonding series. In this case, we're talking about covalent bonds, and this is kind of part 4 of the note series. And covalent bonds, remember, are not givers or takers. These are shares. They are only occurring between a nonmetal and another nonmetal, so only occurring between things on the right side of the periodic table. These are not very strong bonds. We can break them apart on a stovetop. Basically, if you're talking in Celsius terms, their boiling points are generally under 300 degrees C. And you can share multiple sets of electrons. So you can have a single, a double, or a triple bond. Electrons share can have an even sharing and an uneven sharing. We're going to talk about this water molecule in just a moment, but you're going to notice that there's a slight charge here. And that's because oxygen, if you think of it as like Jupiter compared to the Earth, Jupiter has way more gravitational pull because it's just so much bigger. And that's how I like to think about atoms. Kind of oxygen is the big old Jupiter in this case, and hydrogen is the little Earth. And so oxygen just kind of wins. And most of the time, even though they're sharing this one hydrogen electron with this oxygen and this one hydrogen's electron with this oxygen tends to hang on to them just a little bit more. Every once in a while, they'll go around there, but the bulk of the time they're here. That makes this side slightly negative. But the hydrogen sides then become slightly positive, and that is a charge. It has a slight charge to it. And we call that a polar covalent bond. Unequal sharing gives us polar. Equal sharing gives us not polar. It's not polar. It doesn't have any charge. So in this case, if I have two chlorine atoms, both exactly the same side, they come out of group 17, so they have 7 valence electrons. They each only need one more electron, and then they're happy. So they end up sharing in a covalent bond one pair of shared electrons, and they pull on it equally. And you can see these greater than and less than symbols are equal in the opposite direction. So it's equal sharing. Non-polar covalent bond is equally shared electrons. There's no slight charge to it. Where down here, like we showed you with the water, it's slightly uneven in sharing. Again, hydrogen is so small compared to the chlorine, or that it's taking that one electron from hydrogen, and most of the time it's around the chlorine. And if you look at that, this again is unequal. It's less time around hydrogen and more time around chlorine. Therefore, if chlorine has the negative charge a little more often, it becomes slightly a negative side, where the hydrogen not having that negative there becomes slightly positive. Polar covalent has a charge because of unequal sharing. So here's 2 more examples of the same thing. A nonpolar carbon dioxide, if we look, we've got arrows going in opposite directions. They cancel each other out. It's an equal sharing because the pull is equal on both sides. In this case, carbon dioxide, 1 carbon to 2 oxygens, meaning 2, remember, equally share. But our water molecule, again, here's our direction of our charge. It tends to go towards that direction. That oxygen is not stealing, but overly using the electron more than the hydrogens are, and therefore becomes slightly negative. And the hydrogen ends become slightly positive because their negative electron tends to be around the oxygen more often. So again, a polar charge has unequal sharing. It's often directed with either these handy dandy greater than less than symbols in unequal size, or arrows pointing in the direction that the electrons tend to spend more time with, or balancing each other out, equal and opposite. So what is this one? I mean, you can see it right there. It's labeled nonpolar molecule of carbon dioxide. You should have a clue in because our arrows are going in opposite directions and they're the same size. So again, this is equal sharing, no charge, nonpolar. What's this one called with our water molecule? Again, this shouldn't be too hard. The answer is right there at the top. It's a polar molecule. And in this case, we see our arrows going in the same direction, not the opposite direction, therefore showing us that we have a slight charge. The arrows are pointing towards the direction the electrons tend to stay, therefore it's pointing to the negative side. Now, we can have multiple kinds of bonds. We can have a single pair of shared electrons. In this case, hydrogen's got one, this hydrogen has one, and they come together And most of the time, you're going to see hydrogen as an H2 and other things like that because they pretty easily balance each other out. Now, they're the same size, right? So it's pretty much equal sharing. This would be if I went into it saying it's probably nonpolar, but it has one pair of shared electrons. This is a single bond. You'll need to be able to identify this in the test. This is a single bond. Fluorine is in group 17. It needs one more electron. So does this fluorine. Since they're the same size, they are also sharing a single bond. This is one pair of shared electrons. It's a single bond, probably again nonpolar. We know that carbon dioxide is nonpolar because we just talked about it. But carbon has 2 electrons it can give to one oxygen. So it really needed that second oxygen. 2 electrons went to this oxygen, 2 went to this one. So they're sharing 2 pair. This is a double bond. Again, test question. A single bond is 1 pair shared. A double bond is 2 pairs of shared electrons. And in this case, carbon dioxide has 2 double bonds. 2 with this oxygen, 2 with this one. But carbon can also form a whole bunch of single bonds. In this case, fluorine needed one, this one needed one, this fluorine needed one, and this fluorine needed one. So carbon was happy to share it with each of those. Again, probably at this point getting a lot more even because it's pretty much pulling in all directions. But in this case, I've got a single bond here, a single bond here, a single bond, and a single bond. Remember, a single bond is 1 pair of shared electrons. But in this case, this is carbon tetrafluoride because it's got 4 fluorines, and it would be 4 single bonds. But they're single bonds because it's only sharing one with each one. So let's take a look at this. Think this through. Take a look at these pictures and see why we're looking at covalent versus ionic. So now we're going back into looking at ionic. What's the difference between the two when you look at this diagram? What are you seeing and noticing? What should be coming to your head at this point? Well, if you said, okay, look, I've got an arrow showing that this electron went over here. This has electron transfer. It's giving away electrons. This one's taking in electrons. Therefore, we have an ion that forms. The actual individual element or atom, in this case, gets a charge, either positive or negative, and opposites attract. Your positive ion is attracted to your negative ion, and we get an ionic bond. These have high melting points. They have very strong bonds. These are hard to break apart. These are strong bonded things because they give and take electrons. Versus the left side, we don't have that transfer. We simply have shared, and this is a shared pair, a single bond. And because of that, remember, covalent bonds do not have as high of boiling points. They're much easier to break apart. So that's kind of a quick summary of covalent bonds. Covalent bonds can be polar or nonpolar. And if they have a slight charge, then they are kind of attracted. Like water has the ability to kind of cling to the side of things and cling to your finger if you have a drop on it. And that's because it's got a slight charge. So ionic transfer is the giving and receiving of an electron. Covalent is the sharing of electrons. That is kind of it in a nutshell. You need to hit complete. In this case, you're doing an ed puzzle. These notes are always, as always, available on Schoology. You can take a look there. And if you have questions, please ask.